Okay, this is I'll remind myself of that funny joke. Mountains aren't just funny, they are hill areas. Sarah, what do you think of that one? That's good? That's really good. Okay, what are the parts of a kite? A kite has ends, and that's really what we define. And remember, we define kite in 6.3 as two isosceles triangles stacked on top of each other. And that's a pretty good definition, although we would have to eliminate this like diagonal here if we're just going to call it a quadrilateral. The kite symmetry theorem says, what is the symmetry line for a kite? And we'd say the line containing the ends. So we've drawn that here. The kite diagonal theorem, well, the symmetry diagonal of a kite is uniquely related to the other diagonal. It's uniquely related because of the nature of isosceles triangles. So the symmetry line of an isosceles triangle, if we're calling that an isosceles triangle on the top and this is an isosceles triangle at the bottom with a shared base, we've got this is an symmetry line for that isosceles triangle, and this is an isosceles line for this isosceles triangle. So they share one, and as a kite, this means that this is a symmetry line for the kite. Okay, we've used this analogy of like a super shape, and a rhombus is like a super kite. So a rhombus is a super kite because it's a kite in all directions. And I've drawn a little picture here where I've got a rhombus and I've got my kite with the tail this way. That's a legal kite. It's got an isosceles triangle up here, and it's got an isosceles triangle down here where they share this as a base. Or I could turn it and I could say I've got an isosceles triangle up here, an isosceles triangle down here, and they share a base. So this is like a super kite. So our kite diagonal theorem holds true, and it holds true twice. So we could say the kite diagonal or the rhombus diagonal theorem says each diagonal is a perpendicular bisector of the other. I think we already answered the question above. Okay, I asked you to prove that a rhombus is a parallelogram. Let's go ahead and do that. We have rhombus SKJP, and we have our given and our to prove statements. Our given statement is SKJP is a rhombus, and our to prove is SKJP is a parallelogram. Now we have our two columns, of course, conclusions on the left, justifications on the right. Our first one is easy. SKJP is a rhombus. That's given. The second one, we use the kite diagonal theorem. So we're going to say angle 1, I'm going to try and hold my camera very, very still. Angle 1 and angle 2 are congruent. We're going to use triangle PSK as our first isosceles triangle. And we're going to say angle 5 and angle 6 are congruent. And both of these are by the kite diagonal theorem, using SJ as our symmetry line. We can also say angle 1 and angle 6 are congruent. We could really say that angle 8 and angle 7 are congruent, and then if we know those and we know the middle ones are 90, then we're really making the argument about 1 and 6. But for this, the way this is outlaid, we've just said angle 1 is congruent to angle 6 and angle 2 is congruent to angle 5. And we use the kite diagonal theorem again, just using a different line of symmetry, PK, because rhombuses are like super kites. And then we use the TPOC, transitive property of congruence, to say that angle 1 is congruent to angle 5 and angle 2 is congruent to angle 6. And what we did was we set up parallel lines in a sense, and we've said these are parallel because we have alternate interior angles. That's 1 and 5, 1 and 5, and 2 and 6. Both of those are alternate interior angles. If I have congruent alternate interior angles, this implies I have parallel lines. And if I have parallel lines, I can prove that SKJP is a parallelogram, and this is the definition of a parallelogram. Properties of trapezoids. Trapezoids exhibit a funny relationship between the angles that are between the parallel sides of a trapezoid. This is the trapezoid angle theorem. What is the relationship? Well, we say consecutive angles between a pair of parallel sides are supplementary. This is a result of when we said we had a transversal that cuts across two parallel lines. Then we know that this angle and this angle are supplementary. Supplementary means what? It means they add up to 180 degrees. Well, in vision, we've got two parallel lines, and that's what we have in a rhombus. So we say the measure of angle A plus the measure of angle B is equal to 180 degrees, and the measure of angle C plus the measure of angle D is equal to 180 degrees. Okay, isosceles triangles are like isosceles trapezoids, rather, are like isosceles triangles with the top cut off. What theorem did we learn from our lesson on isosceles trapezoids, similar to the isosceles triangle symmetry theorem? Well, we learned the isosceles trapezoid symmetry theorem, which says that the perpendicular bisector of one of the bases is the symmetry line. What says the non-base sides of an isosceles triangle are congruent? And that would be ITBAT, isosceles triangle base angle theorem. Or I think there's a corollary after it, technically. And what theorem says that the non-base sides of an isosceles triangle are congruent? And that's the isosceles trapezoid theorem. The non-base sides of an isosceles triangle are congruent. So if we draw an isosceles trapezoid, I'm struggling to do two things at once, draw and videotape. Here's an isosceles trapezoid. We know that the base angles are congruent. We know that this side is parallel to that side. And we know that this side, the non-base sides, are congruent in length. Rectangles are like super trapezoids, super isosceles trapezoids. Well, they're isosceles trapezoids from all perspectives. So I'm going to draw a rectangle. This is technically just an isosceles trapezoid. But what do I know? I can flip it, and I could discover that these two sides are parallel as well, so it's an isosceles trapezoid in both directions. So it's a super isosceles trapezoid. And the rectangle symmetry theorem is a result of the isosceles trapezoid symmetry theorem, which says that the perpendicular bisector to one of the bases is the symmetry line for the trapezoid. And here I could view this as a trapezoid with these two as bases, and of course I would have another symmetry line. So I've got two symmetry lines in any given rectangle. That's a rectangle symmetry theorem. Okay, my phone ran out of battery. Had to take a little break to get it all hooked up. Okay, what figures are rotation symmetric? A figure is rotation symmetric if you can rotate it between 0 and 360 degrees and the resulting image is the same as the original. Okay, so let's think about reflection symmetry again. We thought about, like, we had a leaf hovering in the wind on a piece of like spider's web, and if I flipped it and it was the same leaf, like the same shape, then it's reflection symmetric. Okay, now pretend you're looking down the top of your spider's thread and you need your figure to be able to rotate between 0 and 360 degrees and be the same. So this is a good example. This figure is rotation symmetric because I can flip it. In this case, 180 degrees. It doesn't have to be always 180 degrees, but in this case it does. It has to go 180 degrees and it's going to be the same thing. Ask yourself, is this figure rotation symmetric? Okay, you've hopefully had a second. The answer is no, this is not rotation symmetric because I flip it any number of degrees and I'd have to flip it 360 degrees for it to be rotated 360 degrees for it to be the same shape. So that is not between 0 and 360 degrees. Okay, hopefully you'll be able to identify figures that are and are not rotation symmetric now. Okay, when does reflection symmetry imply rotation symmetry? Well, our answer here is reflection symmetry implies rotation symmetry when the two reflecting lines intersect. This is a direct result of the fact that two reflections over intersecting lines is a rotation. Okay, so here we have two kinds of symmetry exhibited. We've got reflection symmetry. Obviously, on this equilateral triangle, I've got three symmetry lines, and they all intersect at the same point. So, and the angle of intersection of these lines, of this line and this line, is 60 degrees. So that means it's going to rotate double that, so it rotates 120 degrees. Two reflections in a row is 120 degree rotation. And that we can see here, this is a 120 degree turn. I can turn this thing 120 degrees, and it's going to be exactly the same. It's going to look exactly the same as it did before. And I could keep doing it. This is a threefold rotation symmetry. Hopefully that helps. Chapter 6-7, regular polygons. Okay, what constitutes a regular polygon? Well, I need all the angles of equal measure. This means it's equiangular, and I need sides of all equal length. This means it's equilateral. So you could see the other video on that. Name the regular polygons with sides 3 through 12. First, an equilateral triangle. 3 sides of equal length, 3 angles of equal measure. Equilateral and equiangular. Square, this is both equilateral and equal angle. Four-sided regular polygon. 5-sided is a regular pentagon. 6-sided is a regular hexagon. 7-sided is a regular septagon or heptagon, depends on what your flavor is. Regular octagon is 8-sided. Regular nonagon is a 9-sided figure. Those are hard to draw, so I didn't draw it. Regular decagon, a 10-sided regular polygon. A regular 11gon. This is a clue for how to name any sort of regular polygon that has more than an average or a common number of sides. So an 11gon. And then we jump back into our special names, which is a 12-sided regular polygon, which is regular dodecagon. Okay, be able to find the center of a regular polygon. I don't know why it says theorem there. Should not. Well, you just look for the intersection of symmetry lines, which leads us, you might ask, oh, Mr. Haile, how many symmetry lines does every regular polygon have? And you would say, oh, well, I know through the regular polygon symmetry theorem that an n-sided polygon has n symmetry lines and n-fold rotational symmetry. For a triangle, you go from a vertex to the midpoint of the opposite side, and you can do that 3 times. For squares, I can go from corner, from vertex to vertex, so I draw my diagonals. Those are symmetry lines. It's kind of like a kite or a rhombus. And I can also it's also a trapezoid, an isosceles trapezoid, or a rectangle. So I've got 1, 2, 3, 4. 4 different symmetry lines. Pentagons have 5. It's from every vertex to the midpoint of the opposite base. Hexagons, it's from vertex to vertex and through the midpoints of the opposite sides. 7, 8, 9, 10, 11, and 12. So it follows up forever. Okay, be able to find the individual angle measure of be able to find the individual angle measure of any angle in any regular polygon. Okay, we used for an example of a regular octagon. Octagons have how many sides? They have 8 sides. We use polygon sum theorem, which says n minus 2 times 180 is equal to the total number of degrees contained within my polygon. How many identical angles are in a regular octagon? That's 8. So I say 1080 divided by 8. So this is 8 sides minus 2 times 180, that's 1080. So that's, and then divide that by 8. 8 goes into 1080. 135 degrees for each of the 8 sides. So that process can be applied to any regular polygon. Hope that helps.